Okay, here's an example problem on traveling waves, and this wave has a frequency of 2.4 gigahertz. That happens to be what we use for our Wi-Fi. Okay, so we have a frequency of 2.4 gigahertz and a wavelength of 12.5 centimeters. Let's calculate from that the propagation speed of this wave. And if we're thinking that this is a wireless radio wave, I sure hope that we get 3 times 10 to the 8th meters per second, which is the speed of light. Let's calculate it though. The propagation speed from our equation is the distance traveled, the wavelength divided by the period. But 1 over the period is the frequency, so this is lambda times f. Wavelength times frequency. And I'm going to go ahead over here and write the frequency is 2.4 gigahertz. And I'm going to rewrite this as 2.4 times 10 to the 9th hertz. I'm also going to take the lambda as 12.5 centimeters and turn that into meters and say it's it's a factor of 100 for a centimeter, so I move it over 2 decimal places, 125 meters. These are the numbers I'm going to plug into this equation for lambda and f. And lambda times f here is 0.125 times 2.4 times 10 to the 9th. And when I multiply 0.125 is 1/8. 1/8 of 24 is 3, so 1/8 of 2.4 is 0.3. 0.3 times 10 to the 9th. And we can write this as 3 times 10 to the 8th. And it's a meters per second, which is a velocity, which is in fact equal to the speed of light. It's very much smaller than the speed of light, 0.9999 maybe, the speed of light here on the surface of the Earth due to the atmosphere, but we're going to go ahead and take our radio waves as being traveling at the speed of light. When I did the conversion from 0.3 times 10 to the 9th to 3 times 10 to the 8th, you'll notice that I made the exponent smaller, so I had by a factor of 10, so I had to make the number out front, the mantissa, larger by a factor of 10. I divide by 10 by subtracting 1 in the exponent. I multiply by 10 by changing 0.3 to 3. That's how you double check your work on these things. Okay, let's calculate how far the wave travels in 10 microseconds. So we're given a time t of 10 microseconds. I'm going to write this as 10 times 10 to the minus 6 seconds, or 1e minus 5 seconds. So I went to a larger number on the exponent and a smaller number on the number out front. And we have the equation that the distance is the velocity times time. Okay, meters per second times seconds is going to give us meters. And the velocity is 3 times 10 to the 8th meters per second times 1 times 10 to the minus 5 seconds. And this yields 3 times 10 to the 3rd meters, or 3,000 meters, or 3 kilometers. Okay, so 10 microseconds, 3 kilometers. Now express the propagation speed in meters per microsecond. Okay, V is 3 times 10 to the 8th meters per second. And I want to get the seconds in a microsecond. So I'm going to do a 1 second in the numerator to cancel that one out. And I'm going to say that 1 second is 1 times 10 to the 6th microseconds. Okay, I can multiply any number by 1, and this is 1. 1 second really is equal to 1,000,000 microseconds. And when I do this, the units of seconds cancel out, and I get meters in the numerator, microseconds in the denominator, and I have meters per microsecond. And what I have here is 3 times 10 to the 8th divided by 1 times 10 to the 6th. 8 minus 6 is 2. 3 divided by 1 is 3. So I get 3 times 10 to the 2 meters per microsecond. And this is 300 meters per microsecond. Sometimes we use this value as a convenient way of expressing the speed of light, 300 meters per microsecond. Okay. And it says here next in part D that this is the frequency used for many Wi-Fi systems. Suppose the bit rate for the Wi-Fi is 11 megabits per second. How many periods of this wave are used for one bit? Okay. What we need to do is we need to find the period for one bit, the bit period. Okay, and we're going to find it's much larger than the period of the wave. Okay, and we're going to take their ratio. This is the period of the radio wave. Okay, and we're going to calculate both of those quantities and then take their ratio. All right. First of all, let's calculate the bit period. The bit period is 1 over the bit rate. And we're given the bit rate, RB, of 11 megabits per second, which is 11 times 10 to the 6th bits per second. And I'm going to go ahead and plug that in here, 1 over 11 E6. And if I, on my calculator, type 11 times 10 to the 6th and hit the 1 over X button, I'm going to get 9.09 times 10 to the minus 8 seconds. That's the bit period. That may seem small, but it's going to be much smaller than the period of the wave, which is 1 over the frequency. And the frequency is 2.4 gigahertz. So I'm going to go ahead and plug in 2.4. I think I wrote the frequency as 2.4 times 10 to the 9th hertz over here. So I'm going to go ahead and plug into that 1 over 2.4 times 10 to the 9th hertz. And I'm going to get 2.4 times 10 to the 9th hertz. And I hit the 1 over X button on that. And I get 4.167 times 10 to the minus 10. So it is, the period of the wave is quite a bit smaller than the period of the bit period. And if I take their ratio, the bit period over the period of the wave, that's equal to the number of waves per bit. Okay? And I write 9.09 times 10 to the minus 8 and 4.17, let's call it, times 10 to the minus 10th. And if I put that in on my calculator, and calculate it, I'm going to get 218, 2.18 times 10 to the 2, or 218. And what that means is that as this radio wave is going, it takes 218 cycles of that radio wave in time. I didn't make a very nice radio wave there, did I? In time, the radio frequency wave oscillates 218 times in the time it takes to send one bit at our 11 megabits per second rate. So that's just, hopefully gives you an idea about how our Wi-Fi works. We're going to get a lot more details about how Wi-Fi works moving forward. But that's an idea that there are 218 periods of the sine wave. Let me draw it a little bit better like that, for one bit. And so the question then becomes, well, how do we distinguish one bit from another by sending this radio wave? And what do we do after 218 cycles to tell the receiver that we're sending some different data? And we're going to see that when we study modulation. So I hope that helps. And so I hope this was an interesting problem because it's realistic numbers here. Thanks for listening.